All right, students, let me try one here that I'm probably getting some questions because I think you're going to need some numbers that are throughout the book. You could also, I guess, Google them. But let's talk about number 53. So, chapter 14, number 53, it says this. A person inhales and exhales 2 liters of 37-degree-Celsius air, evaporating about 4, and is that a times? Yeah, 4 times 10 to the minus 2 grams of water from the lungs, and breathing passages with each breath. Okay, so there's our given information. Then we get to question A. How much heat transfers occur just to the evaporation of each breath? Okay, so this is the energy transferred by changing to a vapor from a gas. So this is the latent heat of vaporization. So in terms of mass, well, we're told that one directly, 4.00 times 10 to the minus 2 grams. But how much energy then does it take to evaporate? This is where kind of that first chart's going to come into play. Let me grab the book, and I opened it to page 14, or chapter 14. I guess it's page 482. But they list all the values, and here it is, the latent heat of vaporization. And this kind of actually ties in with the other video lecture I did here. And I'll use the joules this time so we can talk about power in watts. But it's 2,256, and then it would be kilojoules per kilogram. Or we can cross out the 2 Ks and just say joules per gram. And that's probably where I should go since the mass is in grams. However, you'll see that's number 5 on here. And if you go down here, your author says, be careful because the numbers that we're used to, and this actually ties back to the last example, I was looking for a number about 540. It looks like that's 539. But I ended up using the 580 really because jumping down here says if you're not at boiling already, it takes even more energy. In a sense, you got to kind of warm it up and then break the bonds. Now, you don't have to fully warm it up, so it's not quite the same as saying I'm going to warm it up from 37 to 100 and then evaporate it. And so your author is saying at body temperature, 37, the latent heat of vaporization is a little bit more. And there's the 580 that I used. And here it is, 2,430. So that's the number and the reason why I'm going to use a number that is in the footnote, not in the chart. So it takes 2,430 joules to evaporate 1 gram when you're at body temperature, 37 degrees. So like I said, if you were already boiling, this number would be smaller, somewhat smaller, but not as small as you might have thought. Okay, so that alone is our first calculation where it says how much heat transfer occurs just to evaporation. So 4 times 10 to the negative 2 multiplied by 2,430 is going to come out to be 97.2 joules for that 1 breath. All right. So seems like a reasonable number here. Yeah, 97, yeah, okay, sure, seems very reasonable. All right, so let's go on to B. It says, what is the rate of heat transferred in watts if a person is breathing at a moderate rate of 18 breaths per minute? All right, so they're looking for energy per time. And so if we think of our time as a full minute, which I'll write as 60 seconds, then the energy would be this 97.2 joules for each, and I'll put a little b here for breath, and then multiplied by 18 Bs, 18 breaths. So that number per breath times 18, that's the total energy in 1 minute. So divided by 60 makes our joules per second, which is our definition of a watt. So 18 times 97.2 is the numerator, divided by the 60 makes about 29.2 watts of energy that would be coming out of the human body just because we're breathing, just because we breathe in and we evaporate some air. And as we evaporate it, that takes energy. But it's part of the necessity of having our lungs be moist and are able to absorb the oxygen there. All right, so then C says, what does C say? C says if the inhaled air had a temperature of 20 degrees, what is the rate of heat transferred to just warming the air? All right, so here I'm going to write an MC delta T, and here we're going to warm the air from 20 degrees C to 37 degrees C. So another factor when we're breathing is we breathe in the air, and just regular room temperature air, so nothing cold or anything, but you breathe that in and you're going to exhale it a little bit warmer. So that's going to take some body heat out of you. So not only are you evaporating the water, but you're warming the air. Now, maybe the best way to figure out the mass of air you're warming is to write it as density times volume. Because the volume, it's what's given in this problem of how much air, it's the 2 liters that you breathe each time. And so going back, I guess this would be to our fluids chapter, we said that the density of the air was about a 1.25, kind of depends upon conditions, 1.29. Your book listed both of them. I see your author wants us to use the 1.29 kilograms per cubic meter. So I'll go ahead and do that for the density of the air. Now, of course, the volume is the 2 liters, and so I will put 2, but I'll also remember that there is 1,000 liters in 1 cubic meter. So if you're looking at 2 liters, you're 2 thousandths of a cubic meter, right? 1 liter is a thousandth of a meter. So there's the transformation from liters to cubic meters. And so there is multiplied together is the amount of mass. And then we'll need to know the specific heat of the air. And so let's go back to our chapter here. And I think the chapter or the table before this one, this was the heat of fusion and vaporization. A couple pages back, here it is, the specific heats of different substances. And then they have solids and liquids and now gases. So let me come down here to the gases, and I'll pick air. Now they make it sound dry. I don't know what else to do. They're not really saying whether the air is really dry or not. And they give 2 set of numbers. They even give a footnote, and we'll kind of see this in chapter 15, that it depends how you warm up the air. That's why it's kind of hard to list gases. Do you warm it up so that it keeps the same volume or the same pressure? Because there's a slightly different number here. And I'm going to take the idea that it's going into my lungs. The 2 liters is the same volume. The pressure can change, so it's not constant pressure. So it's not this number in parentheses. I think what they want. I think they want us to go ahead and do the 721. So, and then I'll look at the units, but that's joules per kilogram per each degree. So let me write the 721. Let me put in the units of joules per kilogram for each degree Celsius. Maybe I'll scan back here and go, okay, this would be the mass in kilograms, so that's a good unit. And it looks like it's going to give me the energy in joules, so that's good too. And the change in temperature, you can see, is an increase of 17 degrees Celsius. So ultimately, we're going to have the answer here in how many joules in this one breath, okay? Now, maybe I better come back here to see if we inhale temperature at what rate. So it does ask for a rate. So I'll get a number here, but I'll also kind of remind myself this is the energy for one breath. So 1.29 times 2 times 10 to the negative 3 times 721 and then times 17. And so this would be about 31.6 joules. And again, per breath. So again, if we wanted to change this to a rate, energy per time, let's do the same thing. Let's take our 31.6 joules per each breath and then multiply it by 18 breaths. So that's the number of joules for the full 18 breaths. And the 18 breaths, time-wise, took 60 seconds. So I'm going to be left with joules per second, which is watts. Okay, so we've got 18 times 31.6, then divided by 60, and about 9.48 watts is warming the air. So more energy is going into evaporating it, and not a surprise given what we had said, how it takes so much energy to evaporate water. But not a neglectable amount. I mean, this is roughly 30 and this is roughly 10. So this is 1/3. 1/3 of the energy is just warming the air. Well, maybe I'll say 1/4 because 30 and 10 make 40. So this is 10 out of 40. So 1/4 of it warms the air, but 3/4 of it evaporates. So not a small amount, but certainly significant. And then this last part says, D, discuss the total rate that heat transfers as relates to the metabolism. So on this one might be the hardest one to think about, but maybe the most useful one. And I'm going to go way, way, way back to where we were first introduced to energy and energy transfer rates, chapter 7. Okay, so table 3 here says power output, and this gives a lot of different objects, cars, dragsters, lightning bolts. But it was a little bit after that, here it is, where your author was more specific to you guys in the life science and said, hey, let's look at the human body here. And would look at the rate consumption, different activities that a human can be doing. It also lists the oxygen consumption. That's kind of a fun one, but not one we're going to focus on here. And if you take a look, somebody just sleeping is consuming about 83 watts. And so coming back here and saying this is approximately 40. So you're spending 40 here. What does it say? Discuss the total rate of heat transfers as it relates to a typical metabolism rate. So even while sleeping, you're going to be generating and consuming and therefore warming your body at a rate of 83 watts. The breathing at room temperature will take care of roughly half of that. This is roughly 40. So you're able to dispense half of that energy, but you need to get rid of the other parts of it. So you do want some kind of transfer of heat energy out of your body, otherwise your temperature is going to warm up. And of course, any other activity would be just even more. Just sitting and resting is 120. Standing, it's not too much. I think that's sitting in class. Maybe with sitting in class, I'll put the same as, kind of what I'm doing right now, where I'm thinking, I'm flipping pages, I'm doing calculations. So sitting in class might be 210 watts. And so as I sit here and work this solution out, I'm warming my body at 210 watts. And apparently, as I'm talking and breathing, about 40 of it is dissipating. But again, that's kind of minor, so hopefully my body's cooling itself in other ways, like, the conduction and convection from my skin here and my shoes, and particularly my feet and my ears. And in my case, I lose a lot of heat to my bald head. I don't have any insulation. So hopefully all that plays together. So not real sure what to write here, if anything. I'm just going to say that this is not much compared to many, many other activities. And so there's got to be some other form. Now I'll leave it in words there. All right. Hopefully that suffices.